So in this video, we're going to talk about power, and here we're going to talk about electrical power, not mechanical power. So first semester we talked about power is work over time, so it's how much energy there is per unit time. Here we're going to talk about the energy of the electrons, either the movement of those electrons in DC or the movement of energy as the electrons move back and forth in AC. So this is specific to electricity. So energy and power. First of all, most appliances, and you can look at anything that you have at home that has like one of the little bricks, the plug-in bricks, it'll have a sticker of some kind on it. And it always has the number of watts or kilowatts that an object uses in order to run. So for example, this all-in-one printer, scanner, copier uses 1,400 watts of power to run. That means it requires 120 volts out of the wall, and it goes up to a current of 12 amps. So it has a max current of 12 amps, which is huge. So power is the rate at which energy is flowing. So how quickly is the energy going through a wire? How quickly is energy flowing through this machine? And it's measured in watts, just like it was in first semester. Power is in watts, which is W. 1 watt is 1 joule per second. So it's the amount of energy per second, which is the rate. So it's something over time. So joule per second. What this tells us is that a standard 100-watt incandescent light bulb uses 100 joules of energy every second. An equivalent to a 100-watt light bulb in the compact fluorescent is around 16 watts. So this is where you can start seeing that energy savings. Instead of 100 joules of energy every second, the compact fluorescent uses 16 joules of energy every second. So a huge decrease in energy. So our equation to find power is P equals IV. So IV, I is current, V is voltage. So current times voltage gives you power. So how can you get more power? Well, you can change voltage. So increasing voltage can increase power. Now, most of us can't do that because we have standard outlets at 120 volts. We have a battery at 1.5 volts. We have a battery at 9 volts. So we can't really do this, but it's there theoretically. Another way you can do it is by increasing current. So how can we do that? How can we increase current? We can't increase the voltage. We can decrease resistance. So if you decrease resistance, it increases current. So the way you would do that is by the gauge of wire. So thicker wires have smaller gauges, thinner wires have higher gauges. I don't know why, it's just the way that it works. So if you need to decrease your resistance, then you need to increase the thickness of the wire. That's really the only way you can change anything is with the actual wire itself. So change the conductor and change the thickness of the conductor. So here's just a review of metric conversion. So our base unit here is watts. So King Henry died by drinking chocolate milk. Kilo means 1,000. Therefore, a kilowatt is 1,000 watts. So if we have a 1,500-watt toaster oven, then it's the same as 1.5 kilowatts for the toaster oven. So 1.5 kilowatt toaster oven is the same as a 1,500-watt toaster oven. Again, it's just changing the unit. So the other thing that you'll need to be able to do for power is determine how much something costs to run. And to do that, we need to talk about the kilowatt hour. So a kilowatt hour is actually a unit of energy. So your power companies do not sell you power, they sell you energy. But an energy company doesn't sound as impressive as a power company. So it's confusing, but they sell you energy, they don't sell you power. Because power is how much energy you use per second, right? So they have to sell you the energy that you then use in a certain amount of time. So you buy electricity by the kilowatt hour, which is kW.h, so kilowatt hour. And it means that you use 1 kilowatt of power for 1 hour. So now let's do an estimation. We have a coffee maker. The coffee maker has a sticker that says that it uses 1,050 watts to run. A typical charge on a power bill would be 14 cents per kilowatt hour. Again, it's 14 cents per unit of energy. Kilowatt hour is energy. So my question is, you are a coffee drinker. How much does it cost just to run the coffee maker for 1 hour each day? Which makes sense because it has to brew, and then you may drink more than 1 cup, right? So how much does it take to run a coffee maker for 1 hour each day, and how much of your power bill will be just running the coffee maker? Well, step 1 is we have to change these watts to kilowatts. So King Henry died by drinking chocolate milk. So this is our base unit, and then we're going to king, or kilo. So we're going to go 1, 2, 3 to the left. So 1,050 watts is 1.05 kilowatts. Next, we need to take it to kilowatt hours. We're running it for 1 hour. So 1.05 kilowatts times 1 hour per day is 1.05 kilowatt hours per day. Now, if you were running this 24/7, then it would be times 24 hours in 1 day. But here we're only running it for 1 hour. So this is where you might start having adjustments in different problems. So now, how many days are we running it? Well, it's a month, and a month typically has 30 days. So 1.05 kilowatt hours per day times 30 days means we use 31.5 kilowatt hours per month. And then this many kilowatt hours per month has this typical charge. So 31.5 kilowatt hours times the charge per kilowatt hour, 14 cents, means that just running this coffee maker costs us $4.41 each month. Doesn't seem like a lot, but it can add up. Speaking of, here are some typical wattages for different things that are in your house. And so what you can do is you can do this calculation for each thing that runs in your house, and you can see where your power is actually coming from on that power bill. So an electric stove, so that's like, the ceramic tops and all, that's 5,000 watts to use. So if it takes you an hour to cook, then 5,000 watts at an hour a day. Electric heaters, like the space heaters, those are about 1,500 watts. Hair dryers, it's always the number. Mine's a 1,600, so mine requires 1,600 watts of power to run. And so you can see where these things can add up. A clock radio doesn't seem like a lot, but that runs 24/7. So it's 10 watts for 24 hours a day. And it can add up. And that's it.